Yes. Okay. So the last talk of this session is by Michele Governale from the School of Chemistry and Physical Sciences, Victoria University of Wellington, and his title is Boundary States and Flakes of Two-Dimensional Second-Order Topological Insulators. Okay, so you have 45 minutes, but you may want to save some time for questions. Thank you.
Thank you. I'm also aware that I am your last hurdle before dinner, so it's not a nice situation. Lots of and so I'll try to sort of stick with the rules of is it 2/3 talk, 1/3 questions. First of all, I am. Besides that, the university I work, but I'm also a member of the McDermid Institute, and that the McDermid Institute is now a new node of ICAM, and so that's my first ICAM annual meeting, and I'm actually loving it. So thank you so much. That has been a really great week of science, and I don't know, that's awesome. So okay. But without further ado, let me try to share a little bit of this story about boundary states in second-order topological insulators. Okay. So that's the plan for today. I will. So we heard before already about topological insulators, but mostly was focused on the bulk and on topological indices. I will actually focus much more on the surface of these systems, and I will start, of course, with an introduction. It will be a brief introduction. And then I will move to the second part where I will show you two models of second-order topological insulators and show some analytical approach to study basically the boundary states of these systems. And then, and I really want to go to the last part, because the last part is really something that is work in progress. And so as we speak, hopefully my master student is calculating. And so that's something very exciting. It's something that is really work in progress. And so I would really like to tell you a little bit about it. Okay, so since often I run out of time, I'll put the co-workers at the beginning, so that is rather than at the end. And so most of the work has been done by Joe Poata, who's a great master student at UW, and together with Fabio Taddei, who is at Scuola Normale in Pisa. And the people in blue are people with whom I have collaborated about topological materials in the past, and of course all the past discussions and the insights that I had are always important. And actually the last two people are experimentalists, and they are terahertz spectroscopists who are actually doing measurements on nanostructures of topological insulators. They are in Rome. Anyhow, so a very brief nutshell introduction. And first, let's start with sort of standard topological insulator. And I don't think there is that much of a need of an introduction here. So these materials are materials that in the bulk, they have a gap, they are insulating, that's why we call topological insulators. But if we look at the surface, so if the material is finite, and so it has a surface, for example, with vacuum, we find that on the boundary, there are conducting states. And so, for example, if we have a 3D topological insulator, something like bismuth selenide, then what happens is that on the surface, there are basically 2D gapless Dirac fermions. So there are states that have Dirac cones that have linear dispersions on the surface. And those states are actually protected by symmetry. So it's actually not easy to get rid of them. You need to, in this case, for example, you need to break time reversal symmetry to get rid of them. So disorder doesn't kill them. And if you look at 2D topological insulators, those were actually probably the first ones to have been realized in mercury telluride, cadmium telluride heterostructures by the group of Lorenz Molenkamp in Würzburg. If you look at those, it works in a very similar way. It's insulating in the bulk, but then now what you have linear dispersion, linear dispersing edge states, which are actually helical. And this type of state has also been called the quantum spin Hall, because it's like a Hall effect without, but there is no magnetic fields. Here is time reversal. And all of this is quite well understood. And then people talk about bulk boundary correspondence. And basically, what it means is if you have a d-dimensional topological insulator, then it hosts, an S is missing, so grammar mistake, sorry about that, gapless boundary states in d-1 dimensions. So 3D, 2D surface states, 2D, 1D, 1D helical states. Now, theorists have been sort of trying to make new models. So before that, actually a little bit more details. For example, for a typical 3D topological insulator is bismuth selenide. And here on the left, you see the complicated crystal structure. But the way you can understand this material and the way theorists understood this material is you can start, let's say, with atomic orbital on selenium and bismuth, and then you can, and then you can sort of switch on hopping between them, so chemical bonding, and so what happens is your level split, and then you can sort of so since you're a theorist, you can sort of introduce things ingredients one by one. That's an advantage that we have with respect to the experimentalists, where they are given all their meal all at the same time. So we can put one ingredient at a time, so we can switch on crystal field, and we can see that our levels split again. But you see, in this case, here these two levels, the plus and minus, were they are still, they are not, they haven't crossed. So this is kind of the normal order of states that you would have in an atomic insulator. But now if you switch on spin-orbit coupling, what happens is that they cross, and this is that's where you get into this topological insulating states, and that's also why these systems are called systems with gap inversion. Okay, and then what you can do is if you're interested in the low energy properties of this, you can just take these four levels here, the nearest to the Fermi energy, and make a 4x4 model, and that's the so-called effective BHZ model. And then you can work with this model, and it's nothing much more complicated than sort of solving Schrödinger equation, only that you have spinors that have 4 components. And so in principle, your undergraduate students should be able to sort of, it's actually true, should be able to calculate those things.
Question? If you look at the band structure at the gamma point, does it agree with the sequence you've shown here? I'm not familiar with bismuth selenide, but if I look at the band structure
here,
around the gamma point, does it fit with that designation?
I think this is what this gentlemen have done.
I see, okay,
So no,
very good,
that's not me. I'm just
very good,
that's introduction.
okay, good.
That's exactly what these gentlemen have done. So that's okay. So then theorists have said, okay, why can we make something fancier? Can we sort of do higher order topological insulators? And I'm using a slightly different definitions than the one that was used before. And so here the idea is now, if let's say that the topological insulator, the one that we have seen so far in the introduction, let's call it first order. I mean, we could already say that's the standard one, the vanilla topological insulator. So that's what we call first order. And so in 3D, we would have a 2D surface state. And that's what we are showing, here. Now you could imagine that to create a material which we would call second order topological insulator, where a 3D material would, instead of showing a 2D surface states, shows those states at the corners, and those are called hinge states. So in this case would be and this we call 3D, second order topological insulator. We can go further, and we could imagine of making a third order topological insulator, and that would then show corner states. And so the idea is that there is some generalized bulk boundary correspondence. If you have a d-dimensional nth order topological insulator, then it hosts, it bugs me terribly, gapless boundary states in d minus n dimensions. So let's say second order 3 minus 2, we have linear 1D states.
So the phase space for the surface states keeps decreasing, right?
Yes. So now what I want to do is I want to do a 2D second order topological insulator. And in this case, so what we expect the surface state to be 2 minus 2 to be 0 dimensional, so corner states. And I will show here, so the model are not my models, but I've chosen 2 models. And I think it's, and the motivation for these studies is, can we find a very simple way to determine what happens, where do we have corner states, what are the properties of these corner states, something that, something that is actually quite simple and intuitive, and then, can we use the properties of these corner states? So that's the motivation. And so the model that I'm considering is written here. And so we have an Hamiltonian that is made of 2 pieces. One piece that is our vanilla topological insulator, and plus an extra term, which I will specify in a second. So let's first focus on the vanilla topological insulator. And so this is basically the BH set Hamiltonian. And so this can be written in this form. And so let me just focus.
The what Hamiltonian? I couldn't.
Sorry?
What did you say?
BH set. So it's the standard sort of effective Hamiltonian for a topological.
That is shown in the first one.
For a topological insulator. Actually, this is written slightly differently if you really want to be picky, but it's unitary equivalent. So it's the same Hamiltonian.
It's very close to the Hamiltonian for the B phase of helium-3. As an aside, it's almost the same Hamiltonian, which is also topological, by the way.
Yeah.
That's fascinating.
B phase, the B phase.
B phase, yes.
B phase, yes.
The B phase.
So yeah, let me walk through some of the terms there. So I think the first thing to understand is this poly matrices here, the sigmas and the tau. So so this is a Kronecker product of two.
Tau is isospin.
A Kronecker product of 2 poly matrices. The sigma are basically could describe a spin degree of freedom, and the tau usually it's again a poly matrix, but in principle could describe an orbital a pseudo spin, an orbital degree of freedom. And then here we have one term that is basically, if you write this as a matrix, this term is diagonal, and it has some gap and 0, and in the actual, and then some dispersion. This is actually not very. It's important to regularize the problem, but it's not crucial. And then it has these terms here that look like they're spin-orbit coupling type of terms, because we're coupling momentum along x with sigma x, and y with sigma y, and tau x. Okay, so that's our topological, our sort of vanilla Hamiltonian for a 2D topological insulator. And then what you can do is you can, for example, see what happens if you have a finite system, you have an edge. Let's say semi-infinite system, you have an edge, and you can basically find an effective Hamiltonian for the edge. And so what happens is that what you expect is that the effective Hamiltonian for the edge becomes something like this, where you have basically your gapless edge states, which disperse linearly. So that's that's basically this part of the Hamiltonian. And then, so people have written sort of models where these gapping terms can be different forms, and I've chosen 2. And the reason why I've chosen 2 is the first one is actually quite simple. If you look at this, this is like sigma x plus sigma y Kronecker tau z. So it basically describes like a Zeeman field along this 45 direction. And this type of term has inversion symmetry. And then the other gapping term that I've used is this one, which is a bit more complicated, but it was one of the first proposal for second order topological insulator. And this actually has combined symmetry as C4 combined with time reversal. So C4 is not enough, you have C4 and time reversal. That's a very technical slide for those who like the tenfold ways to classify Hamiltonians. They're called Cartan or Outland-Zimbauer classes. This one is in class A3. What it means is, that there is broken time reversal and charge conjugation symmetry, but there is a crystal or a chiral antisymmetry, and in this case, so you have this operator that anti-commutes with Hamilton. So that's just very technical, and I'll leave it there. I don't want to talk about this too much, but for the experts it's actually, so basically in principle, my results are related to this particular class. And so now I'll do something very simple. And it's kind of which will show us how we can understand the corner states. And so I want to do something very simple, and I want to just rotate my orbital coordinates such that my axis, the x-axis gets parallel to the edge, and the y-axis which are called x perpendicular, is perpendicular to the edge I'm pointing out. And so the rotation angle, in this case alpha, basically defines me the direction of an edge. So I'm thinking that I'm having a flake, and every edge of the flake has a, the direction is determined by this alpha. So I can think of doing this coordinate transformation, and that's trivial. So I can transform the Hamiltonian, and I can do this. It's kind of simple, but then what I can do is the fold. And here I'm not expecting you to follow this. I'm just put it up just to show that it's something really simple at the almost undergraduate level. And then what we can do is we can do the following. after we have done the rotation, and I've done the rotation only of the orbital degrees of freedom, but not the spinor, because I want to be able to compare the spinor components and see whether they are the same, you know, what I get. Then I can start by saying, okay, now I take the gapping term to 0 and the k parallel to the edge to 0. And then I know what I get. In this case, I have my vanilla topological insulator, so I get my zero energy edge states, which I can find, and they can be written in this form, and they will have some transverse profile, which is exponentially localized around the edge. This characteristic length scale R0 is determined by the parameters A and M0. This happens only if M0, A divided by M0, so if this sign is negative, we usually take A to be positive and M0, and so then this happens only if M0 is negative, which is when the system is topological. And so I can basically, so this is kind of trivial. I can basically find the edge states of the topological insulator. And now at the, so to speak, gamma point for the edge at the k parallel equals 0. And then I use this as a basis to see the effects of, to diagonalize the full Hamiltonian. And so then I get an effective Hamiltonian, which is very similar to the previous one. Okay, I'm sorry, I'm terrible with this clicking thing. And so I have the linear terms, but now the linear terms, so that would be the topological insulator, just the diagonal ones, but now I have developed here some terms of the off-diagonal that acts as gap or as a mass gap. So it's like having an induced mass in the system, which depends on the direction of the edge. So, for example, in the model 1, the one with the magnetic field, this induced mass depends on alpha in this way, and that's plotted as the blue line. And alpha, just as a reminder, alpha is defines the direction of the edge. M2 is a bit more complicated. It depends, as it is cosine of 2 alpha, and this lambda plus it just depends on parameters of the Hamiltonian. And now we understand why we have corner states, because now what we can do is we can say, okay, now I have 2 edges, and defined by 2 angles, alpha 1 and alpha 2. And if I have an inversion of the master, then I have band inversion. Then it's like going from, you know, one is trivial and the other one is non-trivial. And then I have a corner state. But this model tells us a little bit more, because it also actually allows us to predict how much the corner state decays along the edge. And that's actually, it's this decay length is actually still the parameter A divided by this induced mass out for that edge. So in order to verify this, we basically did a finite difference model and solved it numerically, basically exactly because you know we made the discretization constant small enough that nothing changed. And here what you see is the induced masses are these numbers here in certain units. And so here I have positive, here I have negative. I expect here a corner state, and I have a corner state. Here the induced mass is smaller, therefore the decay length is actually longer, and as we see that this state decays more along this. But we can also have very peculiar situations in which the effective mass becomes very small for a certain direction. And in this case, you see that the corner state it's actually, the decay length becomes very long, larger than the dimension. And so what you get is, you get that actually the corner state is not a corner state, but is delocalized along the entire edge. This is kind of cool. And so, okay, I want to hurry up a little bit. So we understood this, and so then we started playing around with this, with a finite difference methods to somehow corroborate our understandings and see what we get, for example, for convex flakes. And if you get with model 1, the magnetic field one, you can sort of, you always end up with 2 corner states. You can get these situations where you have a state that is completely elongated, and you can move them. In this triangle, here you have them at the base, but here you have one at the apex. And this is just rotating, so to speak, the flake with respect to the direction of the magnetic field. And if you do a square, then again you get always 2. You can always also have the special case. What I get always asked is what happens if you have a circle? And what happens if you have a circle that's kind of trivial in this case is the direction. So it's basically the magnetic field, it's along this direction that defines the symmetry, and then you get your 2 corner states here. But you can see this as a kind of limit of a polygon when the number of sides goes to infinity, and you would see here you have positive, 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 so no corner states here, positive, negative, corner state, negative, 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 no corner state, and so on and so forth. Okay, for model 2, it's kind of interesting because for model 2 you can get situations. I just want to show one case. You can get situations like this, where the induced mass is always the same sign. So you have no corner state. And so what I'm showing here, I'm showing the density of the lowest energy state. But the lower energy state is basically not at 0. It's actually this is very close to the gap. So that's not a topologically protected state, and that's all as expected. Okay. So I have 3 minutes.
Yeah, 15 minutes altogether, so you can
But no,
more time and have less questions.
But I want to sort of, so how do we play around with these things and try to sort of use them, for example, to do mesoscopic transfer? So what I'm imagining now is that I have a system, I have a flake, the green thing is my flake of second order topological insulator, and I attach leads. And now what I'll do is I will consider basically model 1, the one with magnetic field. But since I don't want to rotate the flake, I will just rotate the magnetic field. So my Hamiltonian is the vanilla topological insulator 2D plus this gapping Hamiltonian, and I'll take something. I'll change the name of the constant here. But I've changed, and I've introduced an angle theta, which describes a magnetic field along theta, the blue thing in this picture. And of course, if I remove the leads and I look at what happens to the corner states, if theta is pointing in this direction, then I have corner states here and here. If beta is pointing in this direction, then I have an extended state here and an extended state here, not very visible. I'll tell off the student. And I'm joking, of course. And if it's pointing up, I have an extended state here and an extended state here. The idea here is that then if I have a system like this, and my magnetic field is horizontal, like this, then I would get transmission between 1 and 3. But if I am like horizontal, like this, then the transmission will be switched off. But if I have then the magnetic field is pointing up, then, then I will have transmission between 1 and 2, because I have a connection there. And so this acts as a directional switch. So that's the idea that somehow guided us, and now we need to calculate stuff. So, but before, let's do a two-terminal setup. So two-terminal setup, what we expect is, we expect that if the field is horizontal, I get the induced mass vanishes here. So I get transmission between lead 1 and 2. And if the field is not horizontal or deviates much from the horizontal, and I will explain how much it needs to deviate, then I get 0. And actually, if the Fermi energy is much smaller than the bulk gap, the M0, you can find complete, and if the width of this lead is large enough so that you don't have, sorry, for the leads, I forgot to say, we switch off the gapping term. So the leads are standard topological insulators. So if you have no hybridization between the edge states in the leads, then you can find completely analytical results, which are match perfectly with the numerics. So indistinguishable. And so here, so what you find, okay, you define a length scale of the problem, which is this A, this spin-orbit coupling term, divided by this omega z, which was basically the Zeeman splitting. That defines a length. And now you can calculate analytically the entire scattering matrix, even for finite energy. I'm only showing the result, the linear conductance at t equals 0. And the linear conductance at t equals 0, I'm showing only the formula for this, has the conductance quantum, and then it has this very simple form as a function of the angle theta. And what this describes peaks whenever theta, so this is the black curve, it describes peaks whenever theta is 0, pi, 2 pi, so an integer number of pi's. And the linear conductance is completely suppressed in between. These other curves here are the results for finite energy, and so these peaks becomes broader, and you get some kind of oscillation here. And this oscillation is actually Fabry-Perot. We understand it. And in fact, if you do longer devices, these oscillations becomes bigger, and the peak becomes also broader. But the peak at energy equals 0 is still very, very narrow. Okay, just to finish, it's kind of cool that our understanding is actually really working. And so, for example, for the 3-terminal setup, if I look at the conductance 1, 3, the black line, it goes to 1 when I have theta is equal to 0, horizontal, pi, 2 pi, of course. And when I have half integer values, the conductance between 1 and 3 goes to 0, but the one between 1 and 2 gets activated. Again, we have the full scattering matrix, so we know all the phases of the scattering. We know all the phases due to the reflections, and so stay tuned. Now, the interesting thing is that this is quite robust with respect to disorder, because these are basically due to topology, and it's actually also robust if for imperfections at the contact between the leads and the scattering region, because of and that's basically because of the Klein paradox, because it's basically edge states tunneling into edge states. So it's actually, if you have a potential barrier, it doesn't do that, it cannot scatter them. So that's what we're seeing, but stay tuned, because that's actually work in progress. And as I said, we are just finalizing this. Okay. I am sorry, well, I'm spending 5 minutes more than planned. That's it. Thank you for your attention. These are basically a little bit of a summary of what I showed you, and thank you for your attention.
Thank you. Some questions, so please feel free.
I have just one
Yes, please.
comment/question. So in topological insulators in the higher order topological insulator, when you have a corner modes, unless you have a chiral symmetry, which in actual material you don't have it, these modes are moving towards the ball. So in the model level that you have, you're assuming chiral symmetry?
Yes. In both models, sorry. There you go.
Yeah.
We have that both models have this symmetry sigma z tau x.
So I'm saying that in the real systems, you don't have the chiral symmetry.
In the central part, yes.
Yeah.
In the
And
central.
that's why the corner modes, it's difficult to detect them really through this mechanism of the leads, because they just pushed up the wall.
So I think our plan is not to detect the corner modes. Our plan is to use the fact that you basically have these directions where the induced mass goes to zero, enabling transport.
Any other questions?
So it was, sorry, this was two parts. And so the first part was kind of understanding how all this worked. And the second part was like using this understanding of the effective Hamiltonian to somehow make something that, I don't know, I started many years ago with a lot of this mesoscopic transport. So somehow connecting it to that past history was something that was appealing. Sorry.
Yeah, I just wanted to comment. I think that this is, first of all, very pedagogical. Thank you for a very nice talk. I think your explicit analytic models of the surface states are very useful and probably can be used for a lot of interesting applications.
Even for the circle, we have exactly the wave function.
My question to you is, have you thought about calculating the Green's functions? Well, the surface states in particular, presumably they have novel spin structure.
No, but that's a very good.
We've been thinking about this recently in connection with actually some experiments that Vidya has done, which show that you get spin polarized tunneling currents from the surface of samarium hexaboride. I think you could use some of your expressions to help with
I think
that.
this is actually not difficult to do, because we basically have the explicit form of those states.
Is there a question there? Stephen?
Oh, I'm sorry.
Any other question? I have a sort of tangential question. So if I look at the SOTI has, on a 3D, has hinge states,
Yes.
the TOTI will have corner states. So at one point it becomes vanishingly small to be, when does HOTI becomes so small that it's really physically not so meaningful?
I don't think it's meaningful to have something higher than the order of the
system, of the crystal.
But I will also, you have written an entire classification. What is it? An entire but you did a database of all. What was it? No, it wasn't you.
Barry was sitting there.
From my perspective, I've never thought of a higher order HOTI than the dimensionalities.
I think by definition, it's not meaningful.
Yeah. So I never thought about.
Well, you have to go to hyperspace and then.
Yeah.
Okay. Thanks again. That was a great talk. Thanks to everybody.
And we will reconvene tomorrow at